Okay. So once again, your x-axis runs horizontally, your y-axis runs up and down. In a situation where you're asked to find the domain of whether it be a graph, a table, a set of ordered pairs, they're always talking about your x values. So your first coordinates on, if they appear in ordered pairs, it'll be the left-hand side of any table or under where it is labeled as x. Here is a mapping, okay, with the x coordinates appearing first, and here is a graph. Okay, those are mainly the 4 ways on how functions can be represented to you. As we move farther and farther along, you'll see them mostly in the XY plane or in a table view. Okay, but it's very important to understand where they actually hit or where they actually appear. Okay, your y values, they correspond to the y-axis. That is your vertical axis. Okay, negative numbers are from the origin down. Positive numbers are from the origin up. Okay, so here's 10 and here's negative 10. Okay, and in order to understand how functions work, we have to be able to plot points first. So we have the ordered pairs here of -3, 3, 0, -7, 1, -5, 2, and 4. If I want to plot the point -3, 3, I'm going to start at my origin, and once again, I'm counting by 2s, and I'm going to go left until I hit -3. So this dash here is 2 because I'm counting by 2s. I'm going to split these two. So here's -3, and then I have a +3 as the y value. So I need to go up 2 and then find the point 3. Okay, and you can see that little black dot right there corresponds to -3, 3. For 0, -7. Okay, 0 as an x value means that I am staying on the y-axis. Okay, it's not deviating left or right. So I would go on my y-axis. I would go 2, 4, 6, find 7, and plot a point there. For 1, -5, I would start at the origin. I would go right 1, and then I would go down 5 because I have a -5. So 2, 4, -5. Okay, and then for the last point, we have 2, 4. So we would go to the right on our x-axis to 2, and then we would go up to 4 to find 2, 4. And like I said, this is stuff that you should have already done, okay, because it should be pretty basic, pretty easy in an Algebra 1 geometry level class. Okay, where it gets a little foggy is when they ask you to find the domain and range. So if you noticed anything, my ordered pairs, my table, my mapping, and my graph are all consisting of the same exact points. So the beautiful thing is they have all the same domain in all the same range. So my domain, okay, we always start it with a bracket, and then we want to list it, all of the x values, starting at the lowest going to the highest. So if I examine my x's, I have a -3, a 0, a 1, and a 2. Those luckily are already in order. So to answer the question of what is the domain of the relation, we put -3, 0, 1, and 2, and then close it off with a bracket. Okay, and the key thing to remember is that domain talks about your x values. It's what moves horizontally in the xy plane. Okay, similarly, you have what is known as the range. The range is talking about the other half of your coordinates. Okay, so if domain consists of strictly x values, your range consists of strictly y values. Okay, once again, your y-axis is your vertical axis, determining how high or how low you go. It'll appear as the second number in any ordered pair, typically the second column in a table, the second number in a mapping. Okay, so once again, these are all the same, but when I'm analyzing my range, the same way that I listed domain in smallest to greatest, I want to list my range as smallest to greatest. So if we look at my y values, I have 3, -7, -5, and 4. Okay, so my range for this relation is -7, -5, 3, and 4. Okay, domain and range will be a big part of the early chapters. So we have to understand it. Domain talks about your x values, range talks about your y values. Okay, that'll be some of the most common questions that you get today. All righty. But the next question that they're going to ask, and at the very bottom of P4, you'll see the definition, is it a function? Okay, and what it means is if it's a function, it's a special type of relation where each item of the domain maps to a single item of the range. Okay, so in other words, we don't have -3 repeated twice as an x value with a different y value. Okay, there's this thing called the vertical line test. Okay, meaning that if I can draw a vertical line through any given point, I only intercept my graph or my relation at one time. Okay, I don't intersect 2 points. So if we're looking here, we have -3, 3. That's fine, it's just a relation. We have 0, -7, passes the vertical line test. We have 1, -5, and we have 2, 4. It's easier to be illustrated on the graph, whereas if I draw a dotted line through each one of my points, you can see that I'm not going to touch any of my other points. Okay, that's what's known as a one-to-one relation, that each component of my domain maps to a single component of my range, okay, or a specific component of my range. All right, where you run into issues is if I add to this mapping here, okay, so I have -3, 3, 0, -7, 1, -5, and 2, 4, it would not be a function if this -3 also mapped to the y value of 4. So the same way that we went over, we go over 2 to -3, and if there's another point here, so this is -3, 4, this is -3, 3, you can see that by drawing a vertical line, I touch more than one point of my graph or my relation. Okay, that's clue 1 that shows that it's not a function. Okay, and that's because x is your input value. It's what's known as the independent variable. It can stand by itself. A y value is known as your dependent variable, meaning that you have to have a specific x value to get to your y's. Where a lot of people get confused is they think because they see a duplicated number in the y's, that means it's not a function. Well, that's not necessarily true, because with a graph of a parabola, where it's that horseshoe shape, you're going to have the same y values, but they have different x values. Okay? Making sense that way? So we always want to pass the vertical line test to determine if we have a function, or if we have a duplicated x value, like -3 and -3, they better map to the same y value. Alrighty? So that a vertical line only touches that relation or graph one time. The next thing we got to talk about is where the coordinates or the quadrants of our XY plane. So over here, you can see that I have a 1, a 2, a 3, and a 4. Okay, it divides the XY plane into 4 equal parts. Okay, and each quadrant has certain tricks or tips that you can follow to make sure that you're placing them in the correct quadrant. So quadrant 1, which is right here, it's in the top right. You are only in quadrant 1 if you have a positive X value and a positive Y value. Okay, it's the only way you can get there, because you need to move right on the X-axis and you need to move up on the Y-axis. So these both will be positive. Quadrant 2 is in the top left. It's this square right here. Okay, and you can see we will only enter into quadrant 2 if we have a negative X value and a positive Y value. Okay, so negative X value, positive Y value puts you into quadrant 2. Quadrant 3, down here. Okay, you can see it goes counterclockwise. 1, 2, 3. We will only end up in quadrant 3 if we have a negative X value and a negative Y value. Okay, it's the only way you can have it. And then quadrant 4 is our last one. You will only enter into quadrant 4 if you have a positive X value and a negative Y value. Okay, I highly recommend writing that down, because the quicker you can relate those, you can place points quickly. Okay, positive, positive, I know I got to go top right. Negative, positive, I know I'm top left. Negative, negative, I'm bottom left. Positive, negative, I'm bottom right in the quadrant 4. Okay, and it's literally the only way you can enter into those quadrants. But then we have these lovely things called axes or axes. Okay, if a point falls on the axis, like 0, 7 here, that is not placed into any quadrant. Okay, so if a point falls upon the axis, you can label it as x-axis or y-axis, but it does not fall into any quadrant. All righty. Okay, give me a second to erase real quick, and then we're going to go over the example. That is example 3 on page P5. Oh, wrong screen. Wrong screen. There it is. Okay. So everybody can see my Algebra 2 book. We're up. We're on page P5. All right. So example 3 on page P5 says, state the domain and range of each relation, then determine whether each relation is a function. So you can see we got letter A, B, C, and D. Presented to us in 4 different ways, but we can handle it each and every way. Okay? So the first thing is I would write down my coordinate pairs. So for letter A, I have 10, 3, 6, negative 2, 7, 4, negative 8, and negative 9. Okay, and the first question it asked me is what is the domain and what is the range? So for the domain of the function, once again, we're only focused on the x values. Okay, and we want to list them from smallest to greatest. Okay, from smallest to greatest. So we have a 10, a 6, a 7, and a negative 8. The smallest out of all those numbers is negative 8. The negative number, naturally going to be smaller. The next smallest number is a 6. Okay? Then it would go to 7. And then it would go to 10. Okay? And then we would do the exact same thing for our range. Our range only corresponds to the y values, though. So we have a 3, a -2, a 4, and a -9. The smallest numbers out of those is a -9. So we would list that first. The next smallest number is -2. Next smallest number is 3. The next smallest number is 4. Okay, but now here comes the tough question. Is this a function? Okay, is this a function? So like I was saying, one of the easiest ways to determine a function, and it's very helpful until you get very good at it, is to plot the points. Okay, plot the points and make sure it passes the vertical line test. So our first point is 10, 3. So I'm going to go out here on my x-axis. I'm going to go up to where 3 is. That point's right there. Okay, I have 6, -2. So I go right on my x-axis to 6. And then I go down to -2. That point's right there. Then I have 7, 4. So I go to where 7 is. Then I'm going to go up to 4. Should be right about there. And then I have -8, -9. So I start at my origin. I go left to -8. And I go down to -9. And once again, I'm counting by 2s on my scale so that I can fit everything. But now I can examine my xy. If I draw a vertical line here, notice I'm not going to intersect any other points, right? So that point passes. I'm going to draw another vertical line here. I don't intersect any other points, so I'm good that way. Draw another one here. Doesn't intersect except for more than once. And then I draw a vertical line there, and you can see that all of my vertical lines, they run parallel to each other, which means that they never intersect. So this would pass the vertical line test. So we could call this, yes, it's a function. Okay, and that's the vertical line test. That's where you have to pass. Okay, I always do the vertical line test, and it might take you a little bit to get the hang of it, but once you get the hang of it, you can visualize it. Part of mathematics is being able to visualize. Okay? Making sense? Now if we go to B, okay, we're given the points, and it's in table form. You can see that my x value of 1 corresponds to 3 and 4. So I'm just going to do it in ordered pairs. But that right there is a hint that this is not going to be a function, but I'm going to show you what it looks like when you actually plot it. Okay, right now I can tell that this one's not going to be a function because 1 maps to 3 and 4. Okay, but we're focusing on the vertical line test, so we're going to make it happen. So I have all my ordered pairs listed. I plot 1, 3. That's going to fall right there. But then I also plot 1, 4. That's going to fall right there. 2, 7 is up here. 3, 4 is here to there. So if you look at my point 3, 4 and 2, 7, those ones are good. They pass the vertical line test. But 1, 4 and 1, 3, if I draw a vertical line, they don't. I touch both the point 1, 3 and the point 1, 4. So this one is not going to be declared a function. Okay? And that's how the vertical line test works. It's very easy. It's very simple. It's one of the easiest ways to determine if you have a function or if you do not have a function. Okay? If it is a function, a single vertical line or all of your vertical lines will only touch the relation one time. Okay, and you're talking, you could break it down all the way into decimals, so small to millions. They still will only touch one time. Okay, if we're looking at C, we'll do the mapping because it's a little bit more difficult to picture. So you can see in the domain, we have -3, 0, 1, and 5. And then in our range, we have -4, -2, 0, and 2. So if we start with -3, that maps only to -4. So that is a point that's good. It passes the vertical line test. Right? If you look at the point 1, that maps to the range value of 2. Once again, it's just 1 to 1, so that one passes. If you look at 5, 5 maps to 0, that one's good. You only have an issue because of 0 mapping to -2 and 0. Okay, at that point, you would have a 0, 0 point here, but you would also have a 0, -2 point, so I would not pass my vertical line test. Okay? So I gave you just a couple seconds to digest that. Looks like I had a couple chats come through, so I'll make sure. We can't see where you're drawing the lines, okay? Okay, Ashlyn, you need to make sure that you're in speaker view, okay? Make sure that you're in speaker view. Make sure your view options are side by side. And then you can expand the speaker box to have it be big enough where you see what I'm sharing and the page. Okay? Or I'll do C again right now because now you should be able to see me, correct? Okay. And also you'll be able to see it in the lecture portion. Okay. So we're working C again. Working C, we've already proved that it's not a function, but here's the reasoning why. So like with everything, I'm a very habit-driven person. I'm very process-oriented. That's kind of why I'm good at math. Because math is a very process-oriented subject. If you stick to the process, you're going to be okay. So the first thing that I do is I always write down my ordered pairs. So I have -3, -4. I have 0, -2. But then I also have 0, 0. I have 1, 2. And then I have 5, 0. Okay, so the first question they ask is, what's the domain? So the domain, once again, is all of our x values listed from least to greatest. Okay, for any duplicates, like these zeros, you only have to record them one time. So the smallest value that I have as an x is -3. Then I have a 0, and I have a 1, and I have a 5. That's my domain. Okay, for my range. Once again, my range is only talking about my y values. We want to list them from least to greatest. So we start with a -4. We have a -2. We have 0. And we have 2. You can see 0 was duplicated. So we only have to record it one time. Okay, no reason to duplicate. Okay, then to make sure it passes the vertical line test, we can plot them. Once again, we can see here that since we have a 0 and a 0, and they map to two different y values, we know it's not going to be a function, but to illustrate the vertical line test, we're going to plot our points. So -3, -4 is here. 0, -2 is here. 0, 0 is here. 1, 2 is here. And then 5, 0 is here. Okay? So now to ensure that I pass the vertical line test, I'm going to draw a vertical line between each one of my points. And you can see that I run into an issue here. Okay, when I drew a vertical line on the x value of 0, I touched the point 0, -2 and 0, 0. Those vertical lines, they extend as far as you can imagine, and they should only touch your relation one time if it is a function. Okay, once again, you can see this from the map. All right, but then we have letter D, and this will be the last example that I go over on this side. Then we're going to talk about FOIL, is letter D, and it is presented to you as a graph. Okay, this is very handy in the sense of drawing a vertical line test because we don't have to plot the points, right? It's difficult in the sense that finding our domain and range is a little bit tricky. Okay, so the first thing I'm going to ask myself, once again, this is letter D on example 3 on page P5. So for your domain, we're looking at our x values, and I want to start from least to greatest. You can see I have grid lines. They are not marked anyway, so I'm going to assume that each grid line is 1 unit. So starting from the left, working right, I can see that I have 1 at -1. Okay, that's the next unit left of the origin. My next value I have on the y-axis, so that corresponds to the x-coordinate of 0. The next one is on the x-axis, but it is 1 unit right of the origin, so that's a 1. And then my next coordinate is 1, 2, 3, 4 as I move to the right from the origin. So my domain for this relation is -1, 0, 1, and 4. My range, we treat it the exact same way we just did the domain, just now we're looking at the y-axis. Since we want to go from least to greatest, we're going to start at the bottom and work our way to the top. So starting at the bottom, I have a point that is 1, 2, 3 units beneath the origin. So that's a -3. Working up, I have another point that is 1 beneath the origin or the x-axis. So that's a -1. Working up again, I have 1 point that is on the x-axis. So that gives me a 0. And then the last point is 2 units above the x-axis. So that is a 2. Okay? So the hard part when you're looking at a graph is really finding the domain and range. Okay, you got to pay attention to how the graph is labeled. Right? So on mine, I only have 5, but if I put a 10 up here, that means I'm counting by 2. And I'll be sure to make my 10s bigger, that way you guys can see it. If it is not labeled, it is safe to assume they're counting by 1 unit. Okay? So now we just have to determine if it's a function. If we were to draw a vertical line through all 4 of these points, would we intersect any of the other points? And you can use the grid lines to verify that, but the answer to that is no. So that means it passes the vertical line test. So we could say, yes, this is a function. Okay? So part of what your assignment is going to be determining domain and range, determining if it's a function, but then it's also going to ask you which coordinate or which quadrant it is in. So using these same points, you can see we have one point that is up in quadrant 1. That is from 4, 2. Okay, we have 2 points that fall upon the axes. One at 1, 0, so that does not have a quadrant. The other one at 0, -3, so that is not in a quadrant. And then the last point at -1, -1 falls within quadrant 3. Okay, so just remember quadrant 1 is in the top right, needs to have a positive for its coordinates. Quadrant 2 is in the top left, will have a negative x value and a positive y value. Quadrant 3 is in the bottom left, it'll have a negative x value and a negative y value. And then quadrant 4 is in the bottom right. It'll have a positive x value and a negative y value. That's your lecture on representing functions. And now we just got to talk about FOIL to make sure that you guys are all aware. So we are going to go to page P6 in the McGraw-Hill textbook. I'm going to work a couple examples, and then I'm going to turn you loose to knock out your homework. Okay, page P6 looks like this. It has FOIL at the top, and you can see it has example 1. So FOIL is a method that we use when we have multiple, or when we're trying to multiply binomial terms. So if we look here on the first example for A, we have x plus 3 and x minus 5, okay? Since they have parentheses around these, we have to treat these as a whole, and we want to use, basically it's using the distributive property twice. We're going to distribute the x against, we're going to distribute the x on x plus 3, and we're going to multiply it to the x and the negative 5 on our second term. So we only use FOIL when we have binomial terms that are multiplied together, just like this. So x plus 3 and x minus 5. Okay, and FOIL is an acronym. It stands for first, outside, inside, and last. We have x plus 3 and x minus 5 as our first one. Okay. Like I said, FOIL is an acronym. So once again, first, outside, inside, last. The first always corresponds to the first terms. So we have an x, and we're going to multiply that by another x. So x times x is equal to x squared, okay? And that comes from our f. Our O stands for the outside terms. So as you're looking at it, you have an x on the far left side, and you have a negative 5 on the far right side. They're outside. So x times negative 5 is equal to a negative 5x. Then you have your inside terms. You have a 3 and an x that are on the inside. So we take 3 times x is equal to 3x. And then we take our last terms, which are 3 and negative 5. 3 times negative 5 is equal to negative 15. Okay? So at this point, what we would do is combine like terms. So if you look, we have an x squared. If we examine our other answers, no other area shows an x squared. So we cannot combine x squared with anything. So our answer is going to begin with x squared. Now if we take a look at our outside and inside terms, these are the two most common terms that you'll combine, okay? That's because they both have the x variable with no exponent. So those are your only like terms. Negative 5 plus 3 is equal to a negative 2, and we're going to associate our variable with it. Okay, so our answer starts off with x squared minus 2x, and then we have our last term, which came from 3 times negative 5, as negative 15. So our answer here is x squared minus 2x minus 15. Okay, FOIL, multiply your first terms, your outside terms, your inside terms, your last terms, and then combine like terms. Okay, if we do the next example of it, I'm not going to break it down like this. I'm going to make it a little bit quicker, a little bit easier. We're given 3y plus 2 times 5y plus 4. Okay, so once again, multiplying our first terms first. 3y plus 5y, 3 times 5 is 15, y times y is y squared, so we have 15y squared. Then we're going to multiply our outside terms. We have 3y plus 3y times 4. That yields positive 12y. Now we take our inside terms, a 2 and 5y. We're going to multiply those together. 2 times 5 is 10. So we have a positive 10y. And then our last terms are 2 and 4. We multiply those again. And we get 8. 2 times 4 is equal to 8. At this point, we combine like terms, right? We only have one instance of y squared, so we can't combine that with anything else. So we're going to have 15y squared. Here we have a single y associated with a coefficient and a single y associated with a coefficient. Those are like terms, so we can combine those. So our inside terms, 12y plus a positive 10y is equal to 22y. And then we have no other constant to combine. So our answer is equal to 15y squared plus 22y plus 8. Okay. So your problems are all evens. I'm going to just do one more to humor myself and to really beat the issue into submission, and then I'm setting you loose. So if you look at on P6, question 1, we have a plus 2 quantity multiplied by a plus 4. Okay, and like I said, we're going to do the FOIL method. We do FOIL anytime we are multiplying binomial terms together. So a times a, our first terms, is equal to a squared. Our outside terms are a and 4. 4 times a is equal to 4a. Our inside terms, 2 times a is equal to 2a. And then 2 times 4, our last terms, is equal to 8. And then once again, we combine like terms. So there isn't another instance where we have a squared. So a squared will stay. 4a and 2a can be combined to equal 6a. And then 8 is left by itself, so we'll combine those. Okay, it's very easy when you're talking about two positives, so I'll find one that's a little bit more difficult. Here we go. So our answer for number 1 is a squared plus 6a plus 8. And I lied, I'm going to do one more because I want a hard one. We're going to do question number 15, which is 2q minus 17 quantity times a plus 2. Okay, here we have a negative in our binomials, and we have positives. So understand that your multiplication rules are still in effect. A negative number times a positive number will always yield a negative number. Two negatives multiplied against each other always yields a positive number. Okay, positive times positive is always positive. Okay, and then we just repeat the process. Our first terms are 2a and a. Those multiplied by each other, it's 2a squared. Our outside terms, or that's a q, never mind. It's q, not a, dummy. It's q. Sorry. 2q times q is equal to 2q squared. Our outside terms are 2q and 2. Those are going to combine to equal a positive 4q. Our inside terms are negative 17 and q. Negative times a positive always yields a negative. And then our last terms, once again, we have a negative times a positive, and negative 17 times 2 So those are combined to negative 34. Okay, now we're at the stage where we combine like terms. 2q squared, there's nothing to combine it with, so that's 2q squared. 4q and negative 17q can be combined for a negative 13q. And then negative 34, there is no other whole number or integer. So our answer is 2q squared minus 13q minus 34. Okay? Any questions on FOIL? Pretty simple, pretty easy. Like I said, it should be stuff that you've touched on in Algebra 1, possibly geometry a little bit. But now it's time to log on to the assignment. I am posting it to Seesaw right now.